Good morning. Okay, let's continue on the line equation here. Okay, so let's continue the line equation and then let's finish it. Okay. This is what we did at the end of the lecture. I didn't quite finish this example. Let's quickly recap that example here. Basically, we were given two equations, two parametric equations, one for a cat, one for a mouse. Okay. The equation written down initially, they are all in the parameter of a t, because here we're using parametric equation to represent the motion of the cat and the motion of the mouse. So both lines here basically representing a trajectory, time trajectory here. So I can interpret this trajectory as a line or a motion with a constant velocity. And constant velocity representing is basically the coefficient of this parameter t here, which is our constant velocity. Okay. So that's constant velocity, and when t equals 0, that's your starting point at here. The first part of the question is whether the cat can catch the mouse. So we look at basically, is there a common time t such that they meet at the same location? You let this x equal to this x, let this y, this equal to y, and then it will turn out there's no common t that can meet the same location. Okay. Then the question here is essentially, can we do something to the cat motion here so that the cat can catch the mouse at here? So to catch it here, when you have a two trajectory, ultimately basically what happens is really doesn't matter what the two trajectory at here, two lines, they will intersect at a certain point, and catch basically means they have to meet at this point at the same time, right? That's basically what it means. So then we'll proceed. Let's calculate what is this intersection point between the two trajectory. In this particular part, and this is what I emphasized, when you calculate the intersection between two trajectories or two lines, in this case right here, you need to make a little bit of change to the initial parametric equation. Initial parametric equation is given all in terms of parameter t, so we have to change the parametric equation to a different parameter here for the two sets of the motion here. Because if you want to solve the intersection point, and you have to have two different basically parameters here, not the same parameter. Right? Same rule apply to 3D curves, right? If you have a z of s at here, a z of k at here, so same thing. Okay, yeah. So then we let x equal to x, y equal to y, and we can solve for value of s and value of k, so that x, y here are all the same. So that basically means find the intersection point, right? So that's how we find when s equal to 3, k equal to 1, the intersection point is p of 2 and a negative 2. Okay, good. So that's how we what we ended up with in the previous lecture at here. Okay? And the next point here is continuing here is what do we do that we can make the cat catch the mouse? So there are two things you could do. One thing is you can change the initial location, or you can change how fast the cat is traveling, the velocity. So we decided let's change the velocity here, right? Let's change to a different velocity. Basically change to a different constant velocity. You're not going to be able to change its direction because this is still the trajectory, and so all we can do is to bump up this trajectory, this velocity here. So we make use of the simple rule when you have a a vector that is in the same direction as the other one, it's basically just a multiple of the original vector. So I did a little bit of redundancy here. So I normalized the original velocity vector and make it into a unit vector. And then I time a constant c, which I don't know what it is yet. Right? That's what I need to figure out. You could still, actually, the student pointed out, you can actually also use this just to c multiplied by the original velocity v, which is also okay. Okay, yeah. But anyway, so let me continue it here. So c times the unit vector at here to give me a new velocity vector. Okay? And this is c value is what we need to find out at what appropriate value c yield a new velocity vector, and then that new velocity vector will make the cat, right, to be able to catch the mouse. And plugging the new parallel vector here into the line equation, that's still the same line equation for the cat, but a different profile motion now, right? Okay, so here is the new line. Okay, not a new line. Here's the new motion, or let's put it here. This is new motion at here, and now we also know that the intersection point is a p of -2 at here. Okay, so the next question point is what's appropriate new value c so that the cat can catch the mouse. Okay, so that's basically a quick recap of what we did in the previous lecture. Let's get back to this line that is here. As we said, catch basically means the cat and the mouse, okay, needs to meet at this intersection point at the same time. Okay, that's basically what it means. Okay, this particular point is this, and then here is our new motion at here. Now, coming back to the way we solve for the intersection point. If you look at this here, the way we solve intersection point, basically we treat both lines as purely mathematical parametric equations. We give a s, give a k here, we solve for the p, right? And we also get a value of s, we also get a value of a k. That makes sense? Right? So you can't change the cat, right? So you can't change the mouse. So the thing we're changing here is the cat's motion at here. So let's think about the mouse for a second at here. Here's the mouse equation. Now I changed the original t to k, right? But if I change it back, if I change the k back to the t here, so for the mouse we have x of t, okay, equal to 1 plus t, and this is -6 plus 4t. Okay, this is your mouse, right? Okay, and here's the k at here, and if I change this k back to the t, and then when k equal to 1 or when t equal to 1, what's the physical meaning? Basically means what? The mouse travels initially from 1, -6, and now when t equal to 1, it ends up at where? At this point p now. That makes sense? Right? So when t equal to 1, the mouse is at the point p, which is 2, -2. So that's the nature of the mouse motion, right? So if you plug in different t, you're getting at a different location here. But what's the point at here now? The point is, if this is a mouse motion, basically we want to catch the mouse. What we want is we want the cat. Okay, we want the cat to be at point P. At what time? At t equal to what time? 1 second. The same time, right? At the same time. Okay? So if you nail down this information now, then the rest is pretty straightforward, because you see this is your cat motion or trajectory at here. We want the cat to be at the point P when t equal to 1. So the next step I'll do is I'm going to substitute the t equal to 1 into this cat line equation, and also substitute x and y for the cat motion to be the coordinates for the point P. So here is basically, which means x equal to 2, which equal to the new cat equation here, so -4 plus c times 2 over root 13 times 1, right? That's t equal to 1. And then y equal to -2 equal to 7 plus 7 minus at the t equal to 1. So you have two equations that are here. You probably feel like, oh, is that gonna? Because I only have one variable here, right? But in this case here, you'll find you have only one solution for the c, which is 3 times root 13. Okay, 3 times root 13. So the c value here is essentially you multiply the c back to here. That's your new velocity vector or parallel vector for the cat's motion at here. So now you can see your new velocity or parallel vector is 3 root 13 times 2 over root 13 give you a 6. 3 root 13 times 3 over this, and there's a negative sign here, so -9, and the z value is 0. So that's your new parallel vector. And then your new equation for the cat will be okay. So that's your new cat motion in here, right? Okay, so this a little bit back and forth here is trying to emphasize, how to interpret a parametric equation. Sometimes you treat it as a pure mathematical, just parametric equation, right? And then sometimes you treat it as, give it a physical meaning. Here's a motion, here's a trajectory, okay, here's how it moves, and that's the differences between these two. Okay. And I'm very glad that at the end of the last lecture, there was a student actually came to, can I interpret this kind of question to a different type of curves? For example, parabola curves. And I said, why do you want a parabola curve? Because I can think of as a missile tracking from one like anti-missile system, right? Basically you want to shoot down the enemy's incoming missile. So then what do, right? You have to basically use your trajectory to meet the enemy's trajectory at the same time. That's how you can shoot down the objects. So that's exactly the kind of the meaning in it here. Okay, yeah. So which is fine. Any questions so far? So good. Okay. All right. So let's continue a little bit more at it here. Okay. I think I have one more example. Just wanted to go over with you. So here is a plane equation given, and also given 2 points. One plane, 2 points. So here is the question in here. Okay, so this is the plane in here. What are the relationship between the 2 points relative to the given plane? So what we mean by that basically means, so you have Q0 could be here and Q1 could be here. So that means both points are on the same sides of the plane, right? Plane is an infinite plane. If you think about 3D space, you can use the plane to basically cut through the whole 3 dimension and then separate the 3 dimension into 2 parts, right? Planes are infinite. Then that literally means, given the 2 points, you can have 2 points on the same side of the plane, or you could have 2 points on the opposite side of the plane, okay? Or maybe even 2 points are all on the same plane, right? They are on the plane, or 1 point is on the plane, or the other point is not on the plane, that kind of situation. So that's what we mean by the geometric relationship relative to the plane given at here. Right. Okay, so let's take a look at how we can quickly determine, right, where are the points relative to the planes. Okay, where are the points relative to the plane? So it could be the same side or opposite side, okay, or even on the plane. Okay, that's all the possible relationships, right? So how do we determine it, right? The easy way to do it is the idea is let's check, right, whether the point is on the plane or not. So you substitute the coordinates of Q0 and Q1 into the plane equation. Okay, you only substitute. In this case here, let's only substitute into the left side of this plane equation. Okay, so sub Q0 and Q1, okay, into just the left side. Okay, just the left side here. And let's take a look at what do we get for the Q0 if we substitute into the left side of the plane. And I get -1 times coefficient 1, and 2 plus 2, and then 4 times 2. Okay, so that's your left side. And for Q0, for Q1, you get basically 1 plus 2 times 3, and 4 times -1. All right. Okay. Let's do a little bit calculation. -1 plus 4 plus 8, 12 minus 1, 11. 1 plus 6, 7, 7 minus 4, 3. So that's what you get for the left side if you substitute into the plane equation, right, for the Q0 and Q1. So what does that mean, right? Now, first of all, as you can see, both of them, they are not the same as the original right side 7. Okay. So that actually gives you a conclusion, meaning neither of the 2 points are on the plane here, right? They're not on the plane. Okay. So if they're not on the plane, then that's the question. Then are they both on the same side, or are they on the opposite side? Which one? The first one or the second one? How do we know? So maybe the same question I will ask you is this. If I give you a line y equal to kx plus b, for example, right? Okay, and then you also be given a point at here. Not sure what this is. Let's say x0, y0, or here is x1, y1. Now you would have exactly the same kind of question, right? Is this point on the top side or this point on the left side? How do you determine that, basically? So if I have this point, this is your y1 at here, and this is your point y on the line at here, you can literally see this y1 is actually what? It's less than the point on the line here, right? So it's less than that, so which is at the bottom. And you can see this y0 at here is more than this y at here, and this y0 is on the top. So coming back to this equation, that 11 is actually greater than 7, and the 3 is less than 7. Okay. So now you can conclude now, so these 2 points are on the opposite sides. Okay, the opposite. Yeah. So because 11 greater than 7, 3 less than 7. If you this one here, you get instead of 3, you get also an 8 or something. So you can actually have both points on the same side. So that's how you can determine the relative relationship between 2 points, okay, and the plane. Okay, now I also want you to exercise yourself at it here, okay? I'm going to speak to this one here. Now, because we conclude now we can find Q0 and Q1 are both on the opposite side of the plane here. I can actually draw a line. Okay. I can draw a line connecting Q0 and Q1. That's you can create a line here. So you can think about it. Now you have the Q0, Q1. Then what will be the line equation? You have points already. You just need a parallel vector, and you can create a parallel vector using Q0, Q1. Right? Then you can create the line equation. Okay. Then the next point I want you to exercise is: can you find the intersection points between this line and the plane? Once you find the line equation, then can you find the intersection point between the line and the equation here? Okay? So this is my my question for you to exercise. Alright, so try this out, okay? Okay, and then finally, before we move on to the new topic here, then also wanted you to think about another 3 geometric relations. So we have learned lines now, we have learned the plane now, okay? And here is the line and the plane relative relationship. Okay. So what I mean by that is, if I have a plane here, right? Let's think about all the possible relationships. You have a line. If I plane it here, and if I also have a given a line here, what's the possible relationship between this line and the plane? You could have what? You can have a line which is on the top of the plane. Okay. And this is a relationship, we call it parallel. Okay, so the line is parallel to the plane. So that's one relationship. Okay. And you could also be like this. Okay, you can also have a line which is on the plane, or the plane passes through the line at here. So that will be the second relationship. That's basically the line is on the plane. And then third one is pretty obvious. Okay. So you can have a line which intersect with the plane. Okay, which intersect. Okay, so that's all the possible relationship here. So here's a question: how can I quickly determine what type of relationship between this given line and this given plane? How do I quickly determine that? So I would just hypothetically, you have a line equation in here. So you have a line equation, and you also have a plane equation. So the simple question, even a multiple choice kind of question: given line in a plane, what's the relationship between these two? Right, 1, 2, 3. How would you quickly determine that? Yes. But your first step will be a very difficult part, transforming the plane into a parametric equation, right? Yeah. So, as a matter of fact, in a future step, when we learn for general surfaces, there is a way to use parametric equation to represent aperture surfaces in a 3D space. There is. But it's different. It's different from the parametric equation for this one. The parametric equation for a line or curve in 3D, it's a function, a set of equations of one single variable. As later you're gonna see, for a surface in 3D, when you use the parametric equation, it's actually become an equation of two variables. So the first step that you wanted to represent this one using a parametric equation like this, that would be probably not very possible to do that. But your second approach, when you're trying to basically substitute the line equation, right, or comparing the two things, that's actually the right thought to do. That's actually the right way to do it. So because you're thinking in that direction, basically, let's check whether it intersects or not, right? If it intersects, then naturally it's not parallel or on the plane, basically. Okay? Yeah. So then how do we do that, or checking the intersection without transforming this into a parametric equation? Here's x, y here. Now, another thing I think I want you to actually not complicate things is, when you're given parametric equation, what exactly is this x, y, z here? Down to the most simplest concept, what's the x, y, z at here? What does it represent? Yes?
Any point on the line.
Exactly, right? It's just a coordinates for any point on the line. It's just a coordinates at here, okay? But it's in the parametric equation format. So if just any point, if it's just also just coordinates, then why can't we just substitute x, y, z into this plane equation at here, right? Into the plane equation. Let's see if that point is on the plane or not. Okay. So the point here, basically sub x, y, z into plane equation. Okay. Directly. Okay. You don't need to do anything at all to the plane equation. Just substitute into the plane equation. And once you substitute here, so you get a times x naught plus kv1 plus b times y naught times kv2, and then plus c times z naught times kv3. Actually, I should more precisely substitute x, y, z into the plane equation left side. Okay, left side here. Just like the previous question, right? How do I know whether the Q naught point is on the plane or on this top side or the bottom side? Okay. And here's what I want to do too. I substitute this x, y, z into the left side at here. Okay? Yeah. Now, once you substitute into the left side, okay, three different scenarios could happen. Okay, three different scenarios could happen. What are the three? So just look at the left side here. One scenario is, so even though you have a k at here, there's a possibility that somehow when you multiply a into here, b into here, and c into it here, and this a kv1 and this b kv2 and this c kv3. Okay, so these three terms here, okay, they could what? They could actually cancel each other. Okay, so it becomes 0, right? So this could be a possibility. Does that make sense? So here, here is, it could be, okay, it could be this situation. Maybe this is negative 2t, then t and t, negative 2k, k, then when you add them together, you get a 0, right? That's possible. Then if this is the case set here, then you're left with what? Then you're left with ax naught plus by naught and then plus cz naught, which are all constants, right? Given. They're all constants here. And then now you can compare this value, right, versus this d value at here. That makes sense? So if this value is same as the d, what does that tell you?
This line is on the plane.
Exactly, right? It's on the plane. If this value is different from d, that means the line is parallel to the plane. So from here, it's like a drawing programming diagram here. Is this 0? If yes, checking this too. Are they the same? So if equal, on the plane, the line on the plane. If not equal, and line is parallel to the plane. So that's one branch, right? So when this whole expression, which is basically an expression in terms of the k, is 0, then you get these two possibilities. Then what if this is not 0, right? So then basically when you add these three terms together, you get a certain function of t, a certain function of k. So you could be maybe, I don't know, you get a 2k or 3k, whatever, right? It's not completely gone. It's not, it didn't disappear. It's left with something. And if that's the case, and if you think about this whole left side here, you basically will get a certain constant d naught plus a certain value of d1 times k for the left side. And then that equal to the whole right side, capital D, right? So that's your case 1, that's case 1, and then this is case 2, right? This is your case 2 here. So your case 2 left side, right, is a function of original parameter k. But d naught, d1, d are all the known quantity, so you actually will be able to solve for the k1, right? Will be able to solve the k1. So this is actually the third case now, right? Basically, if you get a value of k1 and substitute the k1 back into the line equation, you get a coordinate, and that's your intersection point. So this is how you can quickly determine what's the relationship between the line and the plane. Okay, any questions so far? Yeah. So there's no numbers in here. It's all general expressions. Yes. Yeah, you substitute the k1 back to not a k1, it's a k, right? You substitute the k value, whatever you calculate from here, and back into the line equation in here, and you will get a set of coordinates x, y, z, and that's your intersection point coordinates. Clear? Good. So sub k back into line equation, we get the intersection point. Okay. All right, so that's pretty much the type of question, given a plane and a line, like a different kind of relationship. And I do have a summary in the lecture notes, and I think I'll encourage you to take a look at it. Essentially, what are the possible equations involving lines and planes, kind of hypothetical situations. Most of the type of question are covered by the assignments already. Right? Yeah. And there will be a quiz also slightly different from the assignments, but you'll get to practice that. Okay. By the way, the quiz not going to be next week. Most early probably will be a week after. I will send you guys an email, so it's not going to be a pop quiz. If there's a quiz coming up, I will let you know there will be a quiz next week. Okay, so give you enough time to make a schedule arrangement. Okay, let's continue now to a new topic. Okay, so now I'm going to get away from lines and the planes now, just temporarily. So we're looking at the parametric representation of curves now in 3D space. I have a curve C drawn at here. So the point here is, how can I represent this curve C in 3D space? Just like representing a line, right? Yeah. So truly, this is, if I think of the C as a line, then it's really no new things at here at all, right? Because when we describing a line, we use a set of parametric equation. So for C at here, I can literally use the same idea. I can use a parametric equation to represent a curve in 3D and here. But parametric equation, right, is a set of equation. So when you have x of t equal to something, y of t equal to something, and z of t equal to something. Okay. And as I was asking you, and as Luke, right? Luke was mentioned, down to the bottom point for a parametric equation is it's just give you a set of coordinates, and that coordinates representing a point on this curve C or line. Then x of t, y of t, z of t. So it literally basically just means you have a position vector, okay, representing that point P. A position vector comes from where? It comes from this x of t, y of t, and z of t. Okay. That's a position vector. And if you down to a specific lines, it's the same thing, right? If you draw a line and you put that line parametric equation into the position vector, and you get essentially the parametric representation for the line. So here is the simple concept I want you to actually basically remember. The parametric equation give you, if you look at individual points for different t value, you get essentially different position vectors. Okay, you get different position vectors. This position vector here, okay, and write it down, which is becoming a function of a t, and that becomes the parametric representation of the curve. Okay. And that's the simplest way to represent basically a parametric equation for a curve. So then it backs the question here now. Okay, so I know how it looks like for the parametric equation or parametric representation of a line in 3D space. Then what about the other type of curves in 3D space? How do I get the parametric equation for that particular curve, right? And what does it look like? Okay? So let's take a look at a different type of curves, okay? And also to take a look at the very basic way to what I call to parameterize a curve equation. Okay? Yeah. So let's take a look at the first example. Find the parametric equation if you're given two planes. So this question if I don't teach you under this concept of parameterization, okay, if I going back to the the previous lecture line equation here, this is basically finding a line equation here, right? You have two planes. What's the line equation? What's the parametric equation for the line intersected between these two planes? Two planes give you a line. So think about it. What can you do, right? So when you have two planes trying to find the line equation, so I need to do what? I need to find a point on the line, right? I need to find a point on the line, or I need to basically find a point intersected by the two planes, and also need to find a parallel vector for the line. Okay, so I think you probably did assignments. There's one assignment is very similar here. That approach, essentially you can find the two normal vector and do a cross product, and that results the cross product is the parallel vector to the line, right? Okay, and then you should try to find any point on the intersection here, and then use these two information. You can create a line equation basically. That makes sense? Yeah. But I'm not going to do that way. Okay? I'll show you a different way. So this is actually what I call here. It's called, how do I parameterize? The end results will be doesn't look like the same, but it will be the same. It will be different parametric equation, but it's describing the same line. Okay. So this is the concept here. Parameterize. How do I parameterize it here? Okay. When you think about the end results for a parametric equation is every one of them for a line, right? Every one of them is a function of a t here. Okay, it's a function of t here, and then you have a certain initial point or start z here. That makes sense, right? That's your end results of parametric equation. Okay, and parametric equation is not unique. So which means you could choose any arbitrary points, right? Which, as long as it's on that line in 3D space. So then, technically speaking, let's say for z, the z naught could be what? Could be 0. Okay, so if you think about it in 3D space. The line, ultimately, any given lines, right? Ultimately, any given lines could go all the way down. This is xy plane, and then intersect with the xy plane, and then keep going down, right? And that intersection point, what's the z coordinates for that intersection point? It has to be what? 0, right? That's a possibility. As long as that particular line is not parallel to xy plane. If it's parallel, then you won't be able to have that situation, right? Okay? Yeah. But the point here is that z naught could be 0. And the v3 at here could be what? Could be as simple as 1. Right? Because you can always scale these values at here. So basically means z of t could be just t, right? Could be just t at here. So then back to this question here. This is what I'm going to do. Let's just try out. I'm just going to let z equal to t. Okay, I'm going to let z equal to t here. Because that's a very possible solution, right? Yeah. As long as this one is not parallel to xy plane. If I do this, then these two equations in here become x minus 1 plus 2t equal to 4, and 2x plus y minus t equal to 2. I'm going to move the 2t and the t at here to the right side. That's simple just the upper simplification at here. So now you got two equations, two unknowns. So technically it's three unknowns. There's t at here. But I'm going to temporarily treat the t as if it's a known quantity. Okay? So basically this is symbolic, like the solution I'm looking at now. I'm treating this whole right side as if it's a constant. Two equation, two unknown. Guess what? You can solve for x and y now, right? Solve for x and y. Except that the results for x and y will be a function of t. Okay? You will have the t there in the final results. But I can literally solve for these two. So how do I solve for these two? You just like a typical way you solve for a set of linear equations. If this is equation 1, this is equation 2, I'll add these two equations together first, get rid of the y. 3x becomes 3x plus 6 plus or minus t. Then x equal to 2 minus 1/3 t. And I'll substitute the x back into equation 1 or equation 2 to solve for y. Right? Solve for y. So naturally you'll be able to solve for the y. You get y equal to -2 plus 5/3t. So finally, as you can see, what's my starting point for the z? It's t, right? Putting them together, this is the parametric equation. Okay, this is the parametric equation for the line, basically. So that's a completely different approach, right? From finding line equation, right? In like the assignments you did, given a two intersection plane. And this is your parametric equation. So x, y, z, okay, by doing this. So I want you to understand the general approach here is you started by letting z just to a simple t, and you treat t as a constant, solving for x and y. You get two solutions for x and y, which is function of t, combining back with the z equal to t, and you get your parametric equation here. Okay. Now you may ask is, can I do differently? Can I let x equal to t and then solve for y and z? Can you? Yes, right? And same thing, if you can let y equal to t, solve for x and z, same thing, right? You can also do that. The only difference probably is just end results looks like different, but it's still, you know, different parametric equation, but the same, talking the same trajectory here. Okay, so that's one example of how to obtain a parametric equation or parametric representation of a curve quickly. So the rest of the thing here is similar. We wanted to obtain parametric equation for very typical curves. Okay, very typical curves. Here's x squared plus y squared equal to a squared, and that is a circle. Okay, with a radius of 2, centered around the origin. Okay. And the objectivity here is, can I obtain a parametric equation or parametric representation for this particular circle? So instead of using one single expression in here, can I use parametric equation? Essentially, what will be a x of t, what will be the y of t at here, okay? So that, you know, talking about the same curve, same circle. Okay. Now, before I give you the solution for x of t, y of t at here, I want you to also understand another thing is, when you obtain the results for x of t, y of t, always also remember x of t, y of t is just coordinates, right? They're just coordinates. And it's not an arbitrary coordinates. In this particular case, they are the coordinates for what? For any point on the circle here. So basically means if you substitute x of t, y of t back into the circle, then you should have the satisfaction of that original equation, which is this one. Okay, that's the bottom line. So you're not just trying to find arbitrary parametric. You find parametric equations that actually satisfy or equivalent to the original circle there. So how do I find this x of t, y of t then? Let's use it a slightly different approach at it here to describe this circle. So I'm going to draw the circle at it here, okay? At the same time, I will draw a point A, okay? And then now I'm going to describe the motion of the A at here, okay? Suppose A is moving around the circle, okay, starting at this location and moving it at a constant angular speed or velocity, okay, omega. And that's very typical motion, right? You know, in your first year dynamics, when you look at the particle motion, and that's an angular motion basically. So this kind of question becomes, how do I describe this motion of A now, right? Okay. Angular velocity omega here is a constant. Then for any arbitrary time t, okay, let's say after a certain amount of time t, the A end up at this location P at here. Okay. Because it's a constant velocity omega, then as it's rotating from here to here, if this is theta, then what will be the theta value? Which is what? Because you have a constant angular velocity omega, after a certain amount of t, end up at point P. So the theta must be omega times t. Okay, omega t. So that's your theta here. Now then, once I get the omega, I know what the theta is now, then I would be interested in what will be the coordinates for the point P. Okay, coordinates for the P. And this is your radius A at here. Coordinate P is essentially you project that P, okay, into x, y coordinates, okay, axis. So here is your x, here is your y. Okay. So let's make use of known condition to derive the coordinate x and y. And that's pretty straightforward. If you look at the x at here, using the trigonometry, basic trigonometry at here, you look at this right triangle. I know the length of the hypotenuse A, I know this angle theta, then x equal to what? A times cosine theta, which is A times cosine omega t. And what will be the y? And y is A times sine theta, and A times sine omega t. Okay, if I give you this high school stuff, everybody can do that, right? Yeah. Now, if you combine these two together, look at this. If you combine these two together here, that is parametric representation, or that is parametric equation for the moving point A at here, which is on the circle. And then back to the question, am I doing it right? Is this really the parametric equation for that particular A? How do I verify? How do we do that? Substitute x and y back into this circle. make sure the left side is the same as the right side. So if you do that, you get a squared cosine omega t squared plus a squared sine omega t squared. Take out a squared, and cosine omega t squared plus sine omega t squared equal to 1, right? So that verifies, and that's the right parametric equation. So if you look at these two, nothing new, isn't it, right? But if I give it a name now, it's called a parametric representation for this curve now. Okay? Now, to make it a little bit complicated, okay? Actually, before make it complicated, the omega at here, okay? If you look at the omega here, you can literally let omega equal to anything. Okay? You can let it equal to 2 or 3. Okay? They look different, but when you substitute to back to the curve, it's still the same, still on the same curve. It just representing. It just have a different parametric equation, or it just represent different type of motion, right? Different type of angular velocity. Okay. So now let's make it just a slightly different here. Okay. So this is a parametric initiative. So here is the description. I'll just put it on here. So this one here describes a point starting at A. Okay, starting at A and moving with omega. And which direction is this? Is counterclockwise direction. Okay. So you see, for this parametric equation, it's if I don't look at it as a pure mathematical equation, I'm describing it, right, with a very specific type of motion information. Okay? Yeah. So then the next case I wanted to actually make it different is, how about, let's say, instead of starting at A location, how about if I start actually at the B location? So here's the question here. What would be the parametric equation for describing a point, okay, starting at B, okay, starting at a B and moving with constant velocity omega, same thing, counterclockwise. Okay, still counterclockwise. So very little change. And what would that mean to the parametric equation? Okay, before we solve it, the other thing I also need to understand is really for either A or B, okay, or either this case here, they talk about different motions here, but both of them are actually all on the same same circle, right? Same circle here, or same trajectory. So how do I deal with this kind of scenario then, right? If let's say, let's draw the curve here a little bit again. Okay. So here's the B point. Okay. It's starting at here. Okay. Start here. If you started here, moving at omega, okay, constant angular velocity omega, then naturally you will see, okay, this is your t equal to 0, right? Here's your t equal to 0 point. After a certain amount of t, we're at this location P. Yes?
I actually have a question.
Yeah, go ahead.
Are you representing angles in degrees or radians?
In this case, it doesn't matter. I mean, as long as when you use your calculator, you know which one to use, right? You know, calculator. But most of the time, probably readings in this case here. But when you use a calculator, can deal with that naturally. Yeah. Is that good? Yeah. So starting at the B point, after a certain amount of time, this is at any arbitrary t moment, we end up at this P point. And what's the angle between the B and the P point? What's this angle here? Yes?
Pi plus WT?
Okay, but pi plus WT. No, just this portion. Just this portion, the theta, from here to here. You're started here, moving to the point P at a constant omega after a t amount of time. Not WT, omega t, yes. Right? So theta here is omega t. Okay? Well, I write it as a W, like down here. So omega t at here. So, good. So now you get, this is your theta here now. And then, another thing I think you also want to be clear is, when you describe a certain angle, okay, especially mathematically, there's always a reference point, okay, a reference point. And the reference point in this particular case is always reference to where? To the horizontal axis x at here, okay? So then, if I ask you, then what's the angle from here to here, right? 90 plus omega t. We will use 2 pi over 2 plus omega t. Actually, now I think I need. When I use pi over 2, am I using degree or readings? Yes, right? Yeah. Okay. So now you can see your reference point is always reference to the x-axis here. Then the actual angle, basically the actual angle for the current location P is pi over 2 plus omega t. That makes sense? Right? Now then, if I use the same approach, what will be the x and y coordinates, right? What will be x and y coordinates? You will see that the x is a times cosine pi over 2 omega t, and y equal to a times sine pi over 2 plus omega t. That's your x and y coordinates. And this is exactly the parametric equation describing the point motion, but in this case starting at a B now and moving counterclockwise at a constant omega, which makes perfect sense, right? So if you see, if I substitute t equal to 0, 0 at here, what's the initial angle? The initial angle is 90 degrees, pi over t, right? Yes? Very good point. Can x equal to a times sine and y become a times cosine, right? Yes, it absolutely can. But what does that mean, right? So this is always, I want you to think twice. You know, mathematically it works, but then what does that mean? What does it describe here? Before we move on here, let's do a little bit of simplification here. Simplification, okay? Cosine 90 degree plus omega t can be simplified to negative a times sine omega t. And this one can be simplified to a times cosine omega t. Okay? So let's spend a little bit of time here. I know it's going to slow me down a little bit. So what does this, how about x equal to a sine omega t and y equal to a cosine omega t mean? Okay. So if you look at this equation here, maybe the first question I should ask is this a valid parametric equation, right? Is this a valid parametric equation? How do I verify? I substitute this one back into the circle here, right? It's a valid, for sure, right? It's valid. Okay. But then if I wanted to relate to exactly what I did here, what kind of a motion does this parametric equation describe actually, right? So here it describes a point starting at here, moving this direction at a constant velocity, right? And this one here, describes a point starting at here, moving counterclockwise at a constant velocity. Okay? So what about this one here, right? What about this one here? Okay. So I'm gonna actually go a reverse direction here. Or maybe let's go forward. So. Okay, so let's look at a different scenario. Let's say here is the initial point t equal to 0. Okay, so here's the initial point t equal to 0. So starting at this point B, in this time I'm going to move it clockwise direction. Okay, move it a clockwise direction with a constant velocity omega. Then what will be the parametric equation describing this motion here, point P, the point motion here? So let's do the same thing, right? If I give it certain time and end up at this point P at here, okay, end up the point P. Now this time it's moving this way, right? Okay, it's moving this way. So for the current point P, so this is how much angle moved. Okay, this is how much angle moved after a certain amount of a t. Okay, but what is the current point P angle reference to the x-axis? So when we're talking about basically, you know, if I give you let's use a vector concept. So here's a vector, right? Here's a vector here. You always reference is what's the angle between the horizontal axis and the vector, whatever you want to call it, r, right? So that's how we always wanted to reference here. Reference always to the x-axis horizontal one here. Exactly, right? So this particular part here is pi over 2 minus theta or omega t. Okay, that's your current angle, right, for that particular p here. Then describing this position point p for the x and y using x and y, then x equal to a times cosine pi over 2 minus cosine omega t, y equal to a times sine pi over 2 minus omega t. That's the actual coordinates for x and y at the point P. And it's not just an arbitrary expression. It actually describes the point P starting at a B, moving at omega, constant omega. And if you simplify this using the trigonometry property, and you get back to this. Is that good? Yeah. So this is a very important point. You know, you're not just learning the math; you're actually learning what's behind the math there, right? Yeah. In robotics, in a lot of dynamic type of an area, you know, you have to come up with a function or parametric equation, whatever you want to call it, that describes certain motion. Right? That's a very, very, very common situation. Okay, excellent. So you can try to think about yourself. You know, if I have a different type of description, right? Then what would be the parametric equation now? Okay. Now let's have another case study here for a circle. Okay, so here's another situation where it's also very common. I'll give you a circle which is in this expression. And as you learned in the high school here, this basically means It's a circle centered around x0, y0, and with a radius of a. Okay, that's a different circle, just different location. Then what will be the parametric equation for this circle then? Okay. I'll write down this solution in here. Okay. You will see why it makes sense. Okay. So here's a solution, a possible solution for the parametric equation for this describing this circle here. Without x0, y0, we learned already, it's a cosine or a sine. The omega can be any values. With x0, y0, actually the only change here, you see the x of t with the starting point x0, y0 at here, and a cosine t, a sine t. So this particular equation actually describes a point starting at this location at here, and then moving around this circle, okay, with an omega equal to 1, right? Omega to 1 here. So you can literally say, okay, if I have a different motion, right, different type of motion, different starting point, then this set of equation will slightly change, right? Will definitely slightly change. Okay. How that changes, just like what we did, that changes just like that. Okay. Okay, good. Another type of equation in here is this, okay, and that's an ellipse, okay, very typical 2D curves. Okay, it's an ellipse at here, and it has a major axis and minor axis A and B. Okay. So you could have a completely similar situation. Maybe I have a point P starting at this location A, and then moving at a certain angular speed omega, right? That's very similar description. So the difference is, because you have a square, b squared here is not a circle anymore. The parametric equation in this case here is, you can use it as a times cosine t, and then y is b times sine t. See the coefficient, right? That's different. Okay. For a circle, you get the same coefficient a, which is the radius. But now this ellipse, here is a, here's a b. Okay. Because if I substitute, okay, back into this elliptical equation here, okay, if I substitute back here, I needed to satisfy that equation, right? And if you try this, you'll see it's very simple verification. The left side equal to the right side, so that's the right parametric equation. It's all good? Yeah. So this is what I call parameterization in here. So let's take a look at another simple one here. Y equal to x squared. Okay. This is a typical parabola curve. Okay. And that's a parabola curve right here. Can I find a different description, mathematical description, a formula to describe the same curve? In this case here, I wanted to, what I call it, parameterize this y equal to x squared, right? Find a parametric equation. How do I do that, right? What's the typical approach? So in the typical approach for this kind of question is very simple. You let x equal to t, right? Because you're looking for x of t, y of t, and both of them are function of t. So, and y here is a function of x, right? So this is a function of x here. So I might as well just, I'll let x equal to t, and then y will be just simply becomes what? T squared. And then so you basically get a set of equation. Okay. That makes sense? Right? That's your parametric equation here. Okay. If I think of it as a position vector, here is point P, here is a position vector representing that point P. So your position vector R of t at here basically is just a t squared. That's exactly from the parametric equation here. Okay. Now, I still wanted you to think about the meaning, right? Also from the motion point of view. Okay. So if I give you this parametric equation, then what kind of a motion does it describe, right? So you can try that out at t equal to 0. And where is the coordinates? It's at where? 0, 0, right? Okay. At t equal to 1. And where is it? At 1, 1. Okay. Yeah, that's how you actually trying to think in terms of moving points on the curve. So if I look at this one here, so basically means it starts at here, and then it moving in that direction, okay, and then it'll keep going, right, as t increasing. That make sense? Okay. Now, how about if I want it actually differently? Okay, if I want it differently, what if I want it actually is this? What if I want you to find a parametric equation that actually describes this way. So it starts from here and then end up at here. So it's starting, this is your t equal to 0. And let's say this is 1 here. Okay, just like that. This is 1 here. And this is your end point here, which let's say call it t equal to 1. Okay, so when t equal to 0, it starts at here. When t equal to 1, it ends up at here. Right? The point is still on the same curve, but completely different motion now, right? Completely different motion. Then what would be the parametric equation representing this particular curve, right? Or this particular motion? Uh, 1 plus t, you mean? Okay. Like this, right? T squared, yeah. Yeah? Okay. Let's verify. Okay? When t equal to 0, 1, 1, that works, right? When t equal to 1, where is it? So if t equal to 1, in your case, your x equal to 2, y equal to 2, right? It doesn't work. Why? Ah, I heard it. So minus, right? Minus. If this is minus at here, then y should be 1 minus t squared. Right? Excellent. So this is gonna work, right? When t equal to 1, both x and y will be 0. So this is exactly the point I want to establish here. You need to be able to describe, not just know that this is a parametric equation. What kind of motion it actually describes it here? Okay, yeah. What direction is moving? Okay, so let me finish the rest of the work next week. Okay, any questions so far? Yes. Okay.
Can you put boundaries on that?
Sorry.
Can you put boundaries on that?
Oh, excellent. Yeah. A lot of time, yes. Yeah, in this case, I didn't put a boundary. A lot of time, you will see parametric equation t goes from, let's say, 1 to 0 or 0 to 1. You have a boundary for the t. Okay, good. Yeah. Okay, I'll see you next week.